So let's do another example for finding an inverse algebraically. Let's find the inverse of f of x when f of x equals x squared plus 4x minus 5. Oh, so this time f of x is not linear. This time f of x is a quadratic function. We should know right off the top of our heads that a quadratic function is going to look something like this. And so, will this pass the horizontal line test? No, this will not pass the horizontal line test. So, not only do we need to get the inverse function, but we also need to make sure that the inverse is a function. So, we're going to have to restrict the domain of f of x, because right now this does not pass the horizontal line test. But if you only had from the vertex and the right side of the u, you would pass the horizontal line test, and you did not. If you got rid of this part of the u, you did not get rid of any of the range of f of x. You just made a restricted domain so that your inverse is a function. So we need to cut off from the vertex. So what we're going to have to do is we're going to want f of x in vertex form, because not only do we need the vertex, but we need to swap x and y. Right now, you have two x's here. You don't want that. There is a way to rewrite this so that you only see one x. And that's if we write this in vertex form. Remember, vertex form is f of x equals a times x minus h squared plus k, where h comma k is the vertex. So what we can do here is complete the square. Remember from Algebra 2, completing the square, okay, we used it in inverse functions. You also had to use completing the square when you were doing conics this year. So we have f of x equals x squared plus 4x minus 5. Completing the square is going to allow us to have a square of a binomial. That's going to allow us to only see x once, but it's also going to give us the vertex form of this quadratic. So we don't want this minus 5 on this side, so we bring it to the other side. So f of x plus 5 equals x squared plus 4x. Now, we want to complete the square on the right-hand side. So we need to find that value that completes the square, and then whatever you do to the right, you have to make sure you do to the left. So you take half of that and square it. That's going to give us 2 squared. That's going to give us 4. So this is going to be f of x, plus 9 equals x squared plus 4x plus 4. That's the same as x plus 2 squared. So our function in vertex form is x plus 2 squared minus 9. So the vertex is negative 2 comma negative 9. So we know that this quadratic, 4, 5, 6, 7, 8, 9, this quadratic looks like this because a is greater than 0, right? So we know it goes up. So we want to eliminate one side. So I'm just choosing the right-hand side of the vertex. You could technically choose the left-hand side. That's fine. So f of x, what we want to work with is x plus 2 squared minus 9, and the domain of f of x, so that the inverse is a function, we have to restrict to being greater than or equal to negative 2. And so now we're going to get the inverse algebraically using vertex form, not standard form. So the problem would be if I try and get the inverse in standard form. Okay, if I have y equals x squared plus 4x minus 5, and I write it as x equals y squared plus 4y minus 5, you need to isolate y. you can't isolate y if you have a quadratic term with y and a linear term with y. The only way to see y once is to write this thing as the square of a binomial and then get rid of that square. So you can either do it in all the way after you've got the y's, or you can just take care of it right here, and it's more efficient to do it here because you need to have the restricted domain. So let's get the inverse. So first I just write as y equals x plus 2 squared minus 9. I didn't do anything yet. I just replaced f of x with y. So now we swap x and y. So this is x equals, in parentheses, y plus 2 squared, square of a binomial. And now we need to get y by itself. So if you didn't do it here and you just had the standard form, this would need to be written in the square of a binomial, and it would give you this. So now we need to get y by itself. So we add 9 to both sides. That gives us x plus 9 equals y plus 2 squared. And we take the square root of both sides. Now I'm taking the square root of an unknown square. So this is giving me plus or minus the square root of x plus 9 equals y plus 2. Y by itself, so we take away 2 from both sides. So that's going to be y equals plus or minus the square root of x plus 9 minus 2. Now, remember what we said. We said the domain of f is going to be x is greater than or equal to negative 2, which means the range of the inverse is going to be y is greater than or equal to negative 2. Now, look at what we have here. Is this a function? This inverse, is this a function? No, this is not a function. If I plug in the number 0, okay, which 0 plus 9, 9, square root of 9 is 3. I have plus 3 minus 2 and negative 3 minus 2. Plus 3 minus 2 is 1. Negative 3 minus 2 is negative 5. But is that in the range of what this is going to be? No. So if I picked the right-hand side of my quadratic, okay, then I picked when the square root, okay, because x is growing from negative 2, my outputs are going to be growing. How are my outputs going to be growing? Because I took away the negative part. So the inverse is just the positive square root of x plus 9 minus 2, where the range is y is greater than or equal to negative 2. Now, if you chose the left-hand side, x is less than or equal to negative 2, you would have crossed out the plus and you would have kept the negative, because you would just be getting, your range would be y is less than or equal to negative 2. So let's do another. Number 3. Why don't we do y equals, oh, no, I'm sorry, not y equals. Find the inverse function of f if f of x is 2 to the x plus 1. So this is an exponential function. And let's see if we remember about exponential functions here. So if we talk about an exponential function, we know that there's a horizontal asymptote, and the horizontal asymptote is going to be y equals 0, and this graph is going to look something like this. Now, this gets closer and closer to y equals 0. It never actually hits 0, but it never becomes parallel. It just gets closer and closer and closer. So does this pass the horizontal line test? The answer would be yes. And so we want the inverse of this. So we know, does this pass the horizontal line? Yes. So we're ready to get the inverse. Y equals 2 to the x plus 1. So swap x equals 2 to the y plus 1. We need y out of the exponent position. How do you rewrite so that an exponent is not in the exponent position anymore? You have to use the inverse of exponentials, which is logs. The equivalent log statement to this exponential statement would be log base 2 of x equals y plus 1. So, if you remember from logs, 2 to the third equals 8. Log base 2 of 8 equals 3. That's what we're doing right here. Now we just got to get y by itself. So we take away 1. So we have y equals log base 2 of x minus 1. We know that this is going to be an inverse equation because 2 to the x, this is the graph of y equals 2 to the x plus 1, passes the horizontal line test. So we use our notation, log base 2 of x, and then minus 1. That is the inverse function of f of x.